Good morning, good afternoon, wherever you may be in your day. Thank you as always for choosing to make general chemistry part of your day. We're going to set the stage for Lewis structures here. We're going to cover one of my pet peeves, and that'll be it. So here we go. Alright, so my pet peeve, and probably this is my background as an inorganic chemist or coordination chemist, is this idea of the octet rule. It's more of a rule of thumb, if you will, kind of like the pirate code. Okay, so what is the octet rule? And I want to go backwards, because a lot of times they say, well, everyone wants an octet because it completes their shell, it makes them like a noble gas, and that's only true for carbon, nitrogen, oxygen, fluorine. As you know, there are a lot more than 4 elements on the periodic table. So what's really going on? What's really going on is atoms are stable when they have an equal distribution of charge or an equal distribution of their electron probability clouds. This truly only happens when all the shells and subshells are completely full, half full, or empty. So these are those are the states we're looking for. Full and empty are a little bit better than half full, but half full also represents a stable point. So if we look at the first shell when n equals 1, remember that's the number of subshells, so we only have the 1s, and to completely fill this shell so everything's full and empty, you would need 2 electrons. So for hydrogen will always have 2 electrons or a single line coming out of it. Hydrogen should look like this forever and ever. Hydrogen with a little dash. In the second shell, and this is really where the octet rule comes from, of course your body is mainly a carbon and oxygen hydrogen mixture and nitrogen, so the octet rule works nicely here for a biological system. Although hemoglobin, you have the iron, and that's not an octet, and you have other things in your body, so it's not generally always true. But when n equals 2, we're looking at the 2 subshells, S and P, 2 to fill the S, 6 to fill the P, or that's where the octet rule applies. And again, this really, truly is only a rule for carbon, nitrogen, oxygen, fluorine. Everything else, it's a rule of thumb. We go to the third shell, 3s, 3p, 3d, total of 18 electrons, so we can go all the way up to 18, and that's fine. Now, octet's still good, because it gives us our full and empty if we get the S and the P, and we leave the D empty. So octet's a nice starting place. But we can go past 8 if we need to. There's nothing wrong with that. So with that being said, that the octet rule is a rule of thumb and not an absolute rule, let's start talking about specifics. Oh, and why 8? If I say why 8, I'll say this in class. I'll probably put this on a test. If I say why 8, I want to say that's how many electrons it takes to fill the S and the P subshells. I don't want, or that creates an equal distribution of electrical charge in the S and P subshells. I do not want anything about the noble gases because it doesn't apply to helium, argon, krypton, or actually it does apply to argon. It doesn't apply to helium, krypton, xenon, or radon. It doesn't apply to the majority of the family. Not a true statement. It fills a shell. Not a true statement. So again, be specific in your word choice. Why 8? That's what it takes to fill the S and the P subshells. It's not what it takes to fill the subshells. You got to be specific. Okay. All right. So how are we going to represent these? And let's just start with valence electrons. And it could not be easier. You literally just go into the periodic table. We're going to ignore it. We're going to pretend the transition metals don't exist. So I'm going to fold over my periodic table right now. And we're going to check out my folding skills. So we're going to have an abridged periodic table. It's kind of like the Cliff Notes. And it's literally just 1, 2, I'll write it right here. 1, 2, 3, 4, 5, 6, 7, 8. There you go. That's how many valence electrons we have. That's my dots they should have. This can't be any easier. 1, 2, 3, 4, 5, 6, 7, 8. And if you look at the family number, and you just do the New Age numbering system where you go 1 to 18 as you go across the periodic table, take the ones place, and the ones place is the number of valence electrons for all the atoms. So you're all set. Not too bad. Or we can just count. Okay. Let's don't ignore the bond thing for right now. Let's go back to what this is. So we're going to represent an electron with a dot, and each side of the letter or symbol is going to be an orbital. So traditionally we think about making a square. We think about the octet rule because that's what it takes to fill the S and the P orbital. So it might be S, PX, PY, PZ. Doesn't really matter which order. But we have those 4 orbitals there, and that's really what's going on behind the scenes. Now remember, hydrogen and helium only have the S. So they would just go together. Helium, all its electrons are paired. It's happy, it's stable. Hydrogen can pair that up with another atom, such as hydrogen, to form H2. And it would complete its shell, and subshell for this matter. But it would complete the 1s. We'd have the 1s, the 2 electrons are in. This is a stable configuration. If we look at lithium, so again, we're talking about covalent bonding, we're talking about nonmetals. This is electron sharing. If we look at lithium, it only has 1 valence electron. Now, it does have s orbitals, it does have p orbitals, but if we really look at lithium, it's only got 1 electron to share. If it shares all of its electrons, that only gets it up to 2. Again, violation of the octet rule. Totally fine. Beryllium has 2 valence electrons. It shares both. That only gets it up to 4. Again, not a violation of the octet rule. It's okay. Boron. And there's some weird chemistry with beryllium and boron because of this, being electron deficient, and where I'll do some bridging things and form some larger structures, but way beyond the scope of this class. If you're curious about does this cause any interest in chemistry, the answer is yes. Okay. Then when we get to carbon, it's got 4 valence electrons. We can put it in the 4 separate orbitals. Remember Hund's rule, we're going to half fill, so we go dot, 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 1 dot on each side. And if we look, carbon can pair up all 4 of it, and now we get that nice octet. Nitrogen, we can't pair up with something that's already paired with its 5 valence electrons. So again, we go around the box with 1s, and then we just go around the box a second time. So we start to pair up. Now there's only 3 there for sharing. Oxygen has 2 for sharing. Fluorine has 1 for sharing, and neon has none. I guess this again is a nice stable picture. So if we wanted to summarize the trend in bonds, this is going to look like something we've already done. It's going to look exactly like the absolute value of our charges from chapter 3. So again, I hope you don't forget what you learned. Number of bonds, 1, 2, 3, 4, 3, 2, 1, 0. That looks a lot like the charges I had you memorize, does it not? Looks an awful lot like that exact same trend, just absolute value. So that's the number of bonds. So you already know this. And one more slide, building into this idea of a Lewis structure. This is a Lewis structure. This is a Lewis structure. I want to talk about some of the characteristics of things you would see. So every atom is going to be represented with a capital letter. You might have a lowercase after it. So you got carbon, oxygen, hydrogen. They're going to be, how the atoms are stuck together will be with lines. Those lines are called bonds. A single line is a single bond. And again, it's electron sharing. 1 electron from A, 1 electron from B, so that's 2 electrons. 2 lines represents a double bond, a bond order of 2. And it's 2 pairs of electrons for a total of 4. So 2 and 2. We get 4 electrons in a double bond. If you had a triple bond, that would be 3 lines. That would be 6 electrons. And then sometimes the electrons are not part of a bond. They're just around the atom. And that would be 2 dots. And that would be called a lone pair of electrons. And they belong to the atom they're attached to. Anything else to talk about here? I don't think so. Oh, if there's a charge, a lot of times we'll put the whole molecule in brackets and they'll put the charge up here. More specifically, you could center it on an atom like carbon if you wanted to. If you want to be specific about where the charge is, that would be a fine way of representing the molecule as well. Sometimes you'll see a picture like this where you got wedges and dashes. Wedges mean it's trying to show you 3 dimensions. It means it's coming out of the board, so this bond would literally be here. And dashes means it's going back into the board, so you can't see it, but if the board was see-through, it would be going back into the board. So it's supposed to look that way. So if you see wedges are coming out of the plane of the paper, if you see dashes, it's behind the paper, and then if it's a solid line, it's on the paper. So, and then sometimes they don't worry about the geometry and they just draw it on the piece of paper. Any other language lingo to talk about here? I don't think so. Counting electrons and how many are around it. You have to pick an atom. So if I pick hydrogen here, there's a single line coming out, and I told you already. You better have 1 line coming out of hydrogen forever. That better be all you ever have. 2 electrons, and this is a 2 electrons only, always, ever, more. Quote the Raven. If we look at oxygen, though, you would count lone pair, lone pair, lone pair, lone pair, bond, bond. 1, 2, 3, 4. Count pairs. Everything's paired up, so count pairs. So we got 4 pairs or 8 electrons. Hey, that's our octet. Woo! And why is it 8? Very good. That's what it takes to fill the S&P subshells. Glad you were paying attention. If we look at carbon here, line, 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 line. 4 lines. 4 times 2 is 8 electrons. Again, octet, why 8? That's right. That's what it takes to fill the S and the P subshells. Lastly, carbon over here. Line, line, line. A couple dots. Again, 4 pairs. 8 electrons. The S and P subshells are filled. I don't even have to ask you anymore. You got it down. Thank you for your time, energy. We'll get into drawing Lewis dot structures, and there's a couple different ways of doing that. I may put up more than one version. Decide which way you like. Stay fantabulous, and see you in class.